in the last few videos in this series, we got a brief taste of the general environment and atmosphere that was in place when Einstein made his breakthrough discovery of special relativity back in 1905. What did we learn? We learned that back in that time, we had really fleshed out the ideas of classical physics, Newtonian mechanics, Lagrangian mechanics, Hamiltonian mechanics, you name it, and we were very confident but complacent in what we had discovered, right? In terms of relativity, it was a very simple, straightforward idea that we had worked out many, many years ago. What we derived in the first video is the Galilean transformation, a transformation that allows us to establish an absolute universal conception between two different perspectives or two different reference frames, right? We are trying to make this absolute conception so that if reference frame A observes something and reference frame B observes the same behavior, we can make their interpretations gel up and make sense, right? To be compatible with one another, right? We wanted this universal conception, okay? So the Galilean transformation allowed us to do that. But what we found when we started doing the Michelson-Morley experiment and when Terence and Philip did their experiment with the lasers, when they shot out the lasers and found that, whoo, this does not extend to electricity and magnetism, what we found is that the Galilean transformation is a limited snapshot of a bigger picture, right? We had only understood how the universe behaves for a small subset of events, right? Events that occur with very low velocities, very low speeds, very low situations that do not encompass everything that could happen in the universe, okay? So the problem that scientists were really experiencing was the fact that Maxwell in electricity and magnetism said light should be constant. But they did not want to believe in that because their well-established ideas and notions, you know, the ideas of classical physics and the Galilean transformation insinuate that if you have some reference frame that's moving really fast, you shoot out some light, guess what? The light observed by somebody stationary should be faster. We fleshed out those ideas in the last video, okay? Now, what we're going to do is we're going to take a look at why Terence and Philip, when they were doing their experiment, why they ran into problems, why the Michelson-Morley experiment, why it changes the face of physics, why it gave us this first breakthrough that had not happened for many, many years, right? Physics was sort of stagnant at that time, okay? So, believe it or not, what Einstein posed and what Terence and Philip had just discovered in their experiment is actually the backbone of special relativity, okay? And by accepting this discovery that light is always constant and asserting this fact, relativistic effects are the consequences that arise by accepting these realities, okay? So what they had just discovered are the two postulates of special relativity, which I have written out and documented here. And again, by accepting these postulates of special relativity, several consequences arise which give birth to special relativity and relativistic effects that we're going to start to discuss in this video, right? So this is a super exciting video. This is going to be your first taste of special relativity, some of the wacky effects that are introduced as a result of it, and hopefully your mind is blown. Hopefully you have a lot of questions. You should, right? Physics should be a discipline in which you question reality. You observe, you do not prescribe. If you learned it last week, you observe, you theorize, and then you critique, okay? So, first let's go over the postulates that were just discovered in Terence and Philip's experiment, or from the Michelson and Morley experiment that Einstein extracted when he was developing his theories. The first postulate, now I'm going to give the exact wording from a textbook. It's going to be a little cryptic, and then I'm going to explain it. Postulate number one states that if a reference frame S is an inertial frame, remember we went over inertial? That's a frame which does not have inertial effects, no acceleration, it's moving at a constant velocity. So again, this is if a reference frame S is an inertial frame, and if a second frame, S prime, moves with a constant velocity, key word here, constant velocity for special relativity, relative to the original frame S, then S prime is also inertial. What in the world does that mean? You probably read that and you're like, woo, I have no idea what that's talking about. But if you dive a bit deeper into it, what it's really saying is that the laws of physics are invariant between frames. Now, in our second video, we went through this experiment with Terence and Philip, and I showed that Galilean invariance is a thing. What was that? Let's refresh your memory. Galilean invariance states that the laws of Newtonian mechanics are going to gel up between reference frames. And we proved Newton's second law, but what this postulate says is all the laws of physics are going to be constant, or they're going to be arising in the same manner regardless of your reference frame, okay? So this is a pretty cool postulate and has a lot of consequences associated with it. One thing which I want you to think about and keep in the back of your head is that if you accept postulate number 1, that the laws of physics are invariant between frames, it means that there is no absolute reference frame. You're like, oh, wait a second, we're trying to find this absolute universal conception of physics. What does that mean? That basically means that if you have two reference frames, one which you think is stationary and another one that is moving, there is absolutely no way to figure out what is the moving reference frame and what is not. I'm going to repeat that again. There is no way to figure out what reference frame is moving and what is not, because this conception of reality, the conception of a moving reference frame, is relative to an observer, right? There is no absolute conception. So let's say we have Philip, he's standing on the Earth, and we see Terence zoom by in a spaceship. Philip is going to say, Terence is moving. But from Terence's perspective, if he's on the ship and he doesn't know a priori that it's moving, it may look as though the Earth is moving away from him, because if there's no acceleration, it may feel as if you're stationary on the ship and you will not know that you're moving unless you had studied this stuff previously, okay? So I want you to keep that in the back of your head, that there's this sort of symmetry, this sort of duality perspective going on here, that you cannot know absolutely who is moving, right? There is no absolute conception of the universe. Rather, it's relative to reference frames, okay? Okay, so that's one big postulate that came out of the observations that Einstein was making, and also from Terence and Philip's experiment. But the big one, which has probably the most significant consequences, is postulate number 2. And this states that the speed of light in vacuum has the same value c in every direction in all inertial frames. What does that mean? Well, this is basically the result we got from the last video, where, we had Terence and Philip conducting that experiment with the spaceship flying away from some stationary, relatively stationary individual. He shot a laser, and they both observed the same speed of that light. Okay, so this is actually something we've tested again and again and again, which we've shown to be true, which we've shown to be the way in which the universe really, I guess, takes the phenomenon of light and transpires it in front of us, okay? So that's how the universe behaves. Now, this guy here, we want to take a look at this. After the experiment with Terence and Philip, they were crushed. They were like, what the hell is going on? We had discovered this nice transformation, this Galilean transformation. It dictates that if we shoot a laser in a moving reference frame, the person who is stationary should observe that the velocity of that light is the velocity of the spaceship plus the velocity of the light. But that was not the case, so they said, I gotta take a step back. I need to observe what is going on in the universe. I need to analyze some of the assumptions I made and try to understand the phenomena that is transpiring in front of me. Remember, again, we do not prescribe how the universe should behave. Rather, we observe what occurs in front of us, study it, and take what we can extract from that observations to develop theories which help to guide us and allow us to predict how things are going to happen in the future. That's how good science is done. That's how good physics is done. And this is what Terence and Philip want to do to try and correct their errors that they observed by not accounting for postulate number 2. Okay? So what did they do? What kind of assumptions did they make in their initial experiment? Well, one assumption they made which I'm going to write out here, is that if you have this very fast reference frame, a spaceship, if you will, and it has a clock, and somebody stationary has a clock, you sync them up right when the reference frame starts to move. What they asserted is that the time, if I get the right marker, the time delta t is equal to delta t prime. In essence, they asserted that time is constant regardless of your reference frame. It's absolute, it's universal. And in an everyday sense, that's something we take for granted, right? If you give somebody a clock, a smartphone, for example, they drive really fast in a car, you would expect their conception of time to be the same as your conception of time. But again, that's a limited snapshot of the full picture of reality, the full picture of the universe. If you dig a bit further beneath the surface, you're going to discover that the universe behaves in very odd ways as a consequence of accepting that the speed of light is constant. Okay? So we cannot assume this. Let's not make this assumption. Again, we're not going to prescribe how the universe should behave based upon what we expect. Rather, we're going to take our notions of the universe, throw it into the trash can, and instead observe and extract what we can from what we observe and develop understanding from that, a rich understanding of the universe. Okay? So, what we're going to have to do is we're going to have to do another experiment. Let's take a look at this assumption. Terence and Phillips say, I do not like this assumption. I'm trying to prescribe reality, how reality should behave. I learned I should not do that from my previous experiment. Let's see if our conception of time is different if we account for this postulate. Okay? So in order to take a look at how time flows, how their clocks are going to tick, if you will, what Terence and Philip do, they develop a new experiment. They take their Star Wars ship from the previous experiment, they take their laser beam, and they say, okay, let's develop our conception of time based upon what we know is real. We know that in any given second, any interval of time, or between any two events that happen, the speed of light is always going to be constant. So let's try to develop our conception of time around that. Okay? So what they do is, they say, okay, I'm going to take that laser beam, and I'm going to have the laser beam have a detector on it. It's going to shoot a laser up to a mirror. It's going to get reflected. It's going to come back, and then it's going to detect that light. And based upon this machine, I can figure out how time is going to progress. I can figure out the length of time between any two events. Those are the key words I want you to remember. Two events, okay? So let me erase this top portion here, and then we can dive into how we're actually going to put this experiment together and see the amazing results it's going to divulge, which are going to have very weird consequences associated with them, but those consequences arise as a fact, or rather due to accepting that the speed of light is constant. So we're going to have two reference frames, a reference frame S, which is attached to the Earth, where we have Philip, and Terence is going to be in the ship. He's going to ride again. He's going to start the detection process where he shoots a flash of light. That's the first event. It gets reflected back, and then when you detect that, that's the second event. So if we're in the reference frame of Terence, S prime, because x prime and y prime has the coordinates, and he's flying at a very high speed, 0.95 times the speed of light, we know that the flash of light and the detection of light are going to occur in the same place. Or that seems plausible, right? If you shoot a laser, hits a mirror and it comes back, you have not moved. Your x and your y of that event have remained constant, right? So x prime and y prime and s prime are not going to change between the flash of light and the detection of light. The light moves, the detector remains stationary. Now, at the same time, we're going to have Philip, he's going to stay on the Earth in reference frame S with x and y, and he's going to enlist his partner, Eric, who's also going to assist with this. And they're going to say that we're going to measure the same exact time, okay, between these two events. I'm going to look at you as you shoot a flash of light. It's going to bounce off the mirror, and when it comes back, I'm going to measure it. So this is a dichotomy. This is a sense of asymmetry between the two, and this is evoked by design and is special. Keep that in mind. In the reference frame S, we need two people because the flash of light and the detection of light do not occur in the same place. I'm going to say that again. The flash of light and the detection of light are not synonymous. They do not occur in the same place. So in order to streamline this effort, you can figure out if this guy, the spaceship, is traveling v relative at a constant speed, which is what we need through the postulates of special relativity, 0.95 times c, we can space out Eric and Philip such that when the light is produced or it is detected, they're at the same exact place and they can stop their own clocks and compare times. Now, in the moving reference frame, things are not super interesting. We say, Terrence is like, I'm going to examine time, I'm going to get this answer. That's why he's happy, that's why he's super excited, and he says, baby, my conception of time is just going to be the length between the detector at the bottom and the mirror at the top, delta y prime, that's d, over the speed of light. Okay, so what did I do here? This is basically, this is delta y prime is equal to c delta t prime. Okay, it's prime because we're in the moving reference frame. Okay, so if we take this and we know that d is the distance between these guys, well, this is just easy. Delta t prime is no more than 2 times d over c. Whoa, what did I do there? So we know that the light has to go up and then has to come back. So that means when it's going up, it traverses this distance d, and then when it comes down, it traverses back down a distance d. So we get 2 times this distance d. We know that the speed of light is c. Again, this is where we invoke the second postulate of special relativity, and we're going to leave that there. So I'm going to put that as a very important result. Little boring. This is what we would observe every day on Earth if we did this experiment. Terrence does this and he's like, oh, baby, I'm freaking happy. Nothing has changed. Maybe our conception of time is absolute. Maybe what we assumed in our experiment is correct, and this is not the source of the problem. Well, lo and behold, we go back to Earth. In that reference frame, we have Eric and Philip here, and they're keeping track of this. And what they say is that, unlike Terrence, the light cannot go straight up. Why? Why can the light not go straight up? Because if it did, it would go up, this mirror would move to the right, and it would miss the mirror. It would not be reflected back. So in order, or rather, the light that is reflected back, that is detected, in order to get a detection, rather, it must move at a slight angle here. So Eric and Philip, they see that the light has to go along this distance here, and it may be longer, it may be shorter. We don't know yet. What we do know is that it's going to travel at the speed of light, and we could take the fact that it has to move at this angle, and we can do some cool geometry stuff, right? Right, we can extract some triangles and do all that trigonometry. So, if we do that, what we find is, I'm going to use a different color. We can say, hey, wait a second here. We're going to have this blue line here, and I'm going to redraw this off of here. I know it's not the best picture. We're going to get this triangle here, and we can form 2 right triangles as follows. And we know that between Eric and Philip, or the time in which the light is flashed and the detection, we know that this whole guy, this is going to be v delta t, where v is v relative. We know that this is moving to the right at a constant speed, so again, it's just what we did up here when deriving this, right? Delta x is equal to v delta t. And we also know, and again, let's back up. I want to make sure you understand this. Delta t, what is delta t? Delta t is the time that is measured by Eric and Philip on Earth, the S reference frame. And we know that when it goes up and comes back down, it transpires the time we're trying to measure. We want to compare delta t with delta t prime and see if this relation is true, okay? And we're doing that by measuring the time transpired, or the time calculated with respect to our reference frame between these two events, okay? So we have v delta t. We know along this guy, or yeah, this leg here, this has to be t, right? This didn't change at all. The distance between here, it can move as fast as it wants. That length is not changing in the y-axis. That's going to remain d. And we know that the length that light travels is going to be c delta t. But to get up to the mirror, to get up here, that's half of the journey, right? Half of the journey. So that should be delta t over 2, right? Right? So this guy is just going to be z delta t over 2, okay? Now, if we take this fact, this reality, and I extrapolate this triangle and draw a prettier picture, what we get is this right triangle. We have d there. Now, one foot of this triangle is not going to be v delta t. Rather, we know that it takes half the time to go up and half the time to come back because we have a constant velocity. So at the point of reflection, this is half of the journey, half of the trip. So this guy should be v times the time that transpires. That is just delta t over 2. Again, from here to here is half the trip. That's half of the time, okay? Same thing we did with this guy up here. So if we take that and go like so, we get this triangle here, and we can do some nice trigonometry, okay? We know that this squared, using the Pythagorean theorem, baby, is equal to this squared plus that squared. So let's do that, okay? So if we do c delta t over 2, we square that guy, the hypotenuse, is equal to v delta t over 2 squared plus d squared. All right, so you're probably thinking, what in the world can we do with this? This is pretty convoluted. Let's massage the equation a bit and see what it divulges. Again, we're taking what we observe in reality, that light is constant, and trying to extract the consequences as a result of that. Do not dictate how reality behaves. Let it behave as it does. Observe it, study it, whoosh, extract understanding out. That's what we're doing right here, baby. Okay, so let's take these squares here and see what happens. So we can have c squared delta t squared over 4. I'm going to move this to the left. Minus v squared delta t squared over 4. And that is going to be equal to d squared. All right, now we want to form some conception of time. So we might want to pull out that delta t at some point. But I'm going to multiply by 4 and pull out the t here. So we get delta t squared is equal to c squared minus v squared. And that is equal to 4d squared. Okay, so now I'm going to do something tricky. I'm going to try to factor out the c squared, and you're going to see why soon. So what we're trying to do, just to make sure you're on par with what we're doing and what the derivations in the book are trying to do, they don't usually give a lot of steps. We're trying to take this guy and compare it to this guy. So in order to get some kind of relation, we need this guy to pop out in this equation somehow. So we're going to need to derive a 2D over c. Okay? We see this, if we take the square root here, that gives us 2d. So we need that extra c, and that's why I'm factoring this guy out. Okay? So what we get is delta t squared c squared times 1 minus this quantity v over c squared is equal to 4d squared. All right, so this guy is going to be important in a second because this is sort of like your relative speed relative to the speed of light, but we'll get there eventually. Now what we want to do is take the square root, and we end up with, I'm also going to divide by d, okay? So we get delta t, the time as measured on Earth, is, I'm going to multiply by the square root, 1 minus v over c, this quantity squared. That's going to be equal to 2d over c. Now, you're probably seeing this connection, and you're probably like, ooh! This is the way in which Terence and Philip can relate their times such that we get this universal, absolute conception between their two reference frames, right? We're trying to compare the phenomena and see if it matches up. We can tell right now it doesn't, which means that some weird relativistic effects are arising, okay? So we want to take this and realize that we can just throw that baby right in there. And what we get is that we get the important result, delta t is equal to, if we divide this, 1 over the square root, 1 minus v over c quantity squared times delta t prime. Ooh, that looks interesting. Now, we're going to simplify this a bit further. I'm going to say that we got a lot of stuff going on here, So I'm going to try to factor this guy out. And I'm going to say this is like delta t is equal to 1 over the square root of 1 minus beta squared, where beta is v over c. That's the relativistic speed relative to the speed of light, times delta t prime. And then we're going to say, I'm going to erase this guy. We're going to put delta t prime. And what I'm going to assert is that we can simplify this a bit more. We're going to call it delta t is equal to gamma times delta t prime, where gamma is equal to 1 over the square root of 1 minus beta squared, and beta is equal to v over c. All right. So, we got this result. What exactly does it mean? It's one thing to do physics. It's one thing to do math. But the real physics is hidden beneath the layers, beneath the interpretation of the results you get. So what in the world is this telling us? This is telling us a very interesting thing. And this is why Philip is freaking out. He's like, oh my God! What did I just figure out? What in the world? And, Eric is just stupid over here. He's just smiling still. He's like, what? But anyway, he's just helping with the experiment. He's a lab rat. What we just discovered is that the time of these events of flashing a light and detecting the light on the rocket, as observed by somebody in reference frame S, or Philip and Eric, that time is different. It's different than the time observed by Terence. Whoa! Wait a second. This seems really weird, right? In everyday language, everyday observations, this is something that would not easily arise, right? Time is time. It flows, at a constant rate. However, remember what I said, our Newtonian perspective of reality is limited. It's a limited snapshot of a bigger picture. If you dive beneath the surface and start analyzing the universe at different situations, or rather in different circumstances, what you find is that special ideas arise. And this really is a consequence of accepting the fact, which we have observed through many, many experiments, that light is constant, right? The consequence that arises is that the flow of time is different from different observers, all right? And what I'm going to say is this factor here is the factor that determines how it's different, and it's a function of the speed of that reference frame, okay? So this guy is known as a Lorentz factor. And what we're going to do next is we're going to take a look at how this changes our conception of reality, what other consequences it has, and some other interesting ideas. Stay tuned.